Welcome to our YouTube channel. In this video, we are going to discuss about stage 2 out of 6 for substation gantry structure loads using European standard EN 50341 part 1. In this, we are going to discuss about the temperature, reliability level, wind parameter, wind pressure and ice parameters, mean and gust wind load comparison and its response factors, structural resonance factors, drag coefficient. So after feeding all the input and the data, we need to calculate wind and ice loads. So this is as per EN 50341 part 1. In this first input, we record environmental load parameters is the temperature load, that is minimum temperature load. This is as per project specifications. Here we can consider minus 40 degrees Celsius. Next one is wind parameters. For that, reliability level should be fixed first of all. So the definition for reliability level we can find out in page number 38. So here it is given the reliability level 1 means it is 50 years of return period T of climate actions. For 2 it is 150 years and 3 it is 500 years. So based upon the return period we need to select this 1, 2 and 3. Next one is reference wind speed category. So this again it is as per project specifics. You can consider here as 25 meter per second. Terrain category we need to refer table 4.2.1 of 50341 part 1 page number 49. So here you can see there are 5 number of terrain categories. Also the definitions also given in the next column, second column. So based upon our project location, where it is located in a rough open sea lakes with at least 5 km fetch upwind and smooth flat country without obstacles, or second one is farmland, or third one is suburban or industrial areas and permanent forests, fourth is urban areas in which at least 15% of the surface is covered, and fifth one is mountainous and more complex terrain where the wind may be locally strengthened or weakened. So based upon the project location, we need to select this terrain category, and the density of air is 1.225 kg per meter cube. So that we can find out in page number 50, that is class 4.2.2. Here it is 1.225 kg per meter cube. Terrain factor we need to refer 4.2.1 table. So for that page number 49, here it is KT and Z0 we can take from this table. We are having here in the next tab the table for reference. From there the value of ZO and here this table you can see KT and ZO can be extracted from here in the Excel sheet. So gust roughness factor is Z0. Height exposed above ground, we have already gantry structure model. You can see in our previous video, the link is given in the description. In that we had considered as a 21 meter of gantry height. Wingspan of conductor is 62.5. It is nothing but we are considering the half of both 100 meter and 25 meter, which we had entered in here as input. So 100 meter is in transmission line side and 25 is in substation side. So half of this two is 62.5. Only the half of both the side conductor is going to hold on this gantry structure. So that's why we are considering this. Then next we need to calculate wind speed at height h above ground level. That is this VR2 is a reference wind speed at 10-meter height. So we need to consider based upon our own height of structure. So it is 21 meters our height. So for that there is a formula in class 4.2.2.1.6 of EN 50341, page number 50 to be referred. Page number 49 to be referred. So here is a formula you can see. VH equal to a natural logarithm of h divided by z0 by natural logarithm of 10 divided by z0 equal to kt into natural logarithm of h divided by z2 into vr2. So applying this formula, kt we already having 0.19, natural logarithm into h we are knowing it is 21 meter divided by z0 also we got from terrain category table 4.2.1. So the VH equal to 28.69 meter per second. Next one is a dynamic wind pressure we need to calculate as per class 4.2.2.2. So for that we need to refer page number 50. So here you can see dynamic wind pressure is QH equal to half into rho into VH square. Applying this formula, we are getting 504.16 Newton per meter square. So next one is ice parameter we need to define. Ice type, first of all we need to define what kind of ice is. For that we need to refer table 4.2.6 of EN 50341 part 1, page number 58 to be referred. So here this table 4.2.6 you can see here there are 4 number of ice type: wet snow, glaze ice, soft rim ice and hard rim ice. So we can consider soft rim ice which is having a density as per the table is 300 kg per meter cube. Reference ice load I we need to find out from a national annexers. There are several national annexers, as we said that 50341 part 1 is for general code for overhead line towers or structures, and similarly for 2 and 3 is a part to be referred for national annexers. We need to refer this national annexer based upon the project location countries to find this reference ice I. So we had referred some country where it is having the reference wind speed, sorry, reference ice as 10 Newton per meter. Also this combined factor ice plus snow load also used to defined in national annexes or technical specification of the project. So we need to refer that and we need to enter here as to. Next one is we need to find out the Gust response. To find the Gust response factor, we need to refer table 4.2.2.3 of EN 50341, page 48, 51 to be referred. So you can see here for Gust response, we need to find out the type of wind speed which we are going to use. There are two wind speed, one is mean wind speed, another one is gust wind speed. So the definition for the mean wind speed and gust wind speed are given here. If the retention period is 10 minute at a height of 10 meter above, then it should be called as mean wind speed. and the same the retention period is over 2 seconds, we need to consider as a gust wind speed. So this is also depends upon the project specification or the requirement specified by the client. So if gust wind speed means the entire factors is going to change. Most probably in European nations, in all the European nations, they used to follow only the mean wind speed, because mean wind speed used to have a gust response factor of 1.9, whereas gust wind speed it won't have the gust response factor. So that is the response factor for the gust wind speed is only 1, because this reference wind speed category 2 which we had entered here is a retention period of 10 minutes. So we have to consider only mean wind speed in most of the European nations only, otherwise if the customer specifies to go for gust wind speed. Next is a type of structure we need to define. We know that we are already having a gantry structure model well explained in both robot structural analysis and StatPro. You can find those videos through our link which is provided in the description. So let we consider lattice tower. So based upon these parameters, we need to find out the structural resonance factor. For that, table 4.2.5 to be referred, page number 53. So in page number, so this in page number 51, you can find this 4.2.2.3 class, whereas this mean wind speed to be used means we need to calculate this GQ, that is gust response factor, based upon this formula, or else we can directly get from the table 4.2.4, so which is here. So suppose our height of the structure we had assumed is a 21 meter, right? So for that we need to work out on the table here. You can see the first table stating that this table 4.2.4 is extracted and added here in our Excel sheet. So in this various terrain categories are listed here, and the factors according to the height also entered here. So now we had already selected that our terrain category is 2 here. So for 2, through this interpolation method and VLOOKUP or HLOOKUP option, this factor is calculated and the value is 1.9. So the same is having here. So after this we can go for structural resonance factor. So for that, for a conductor, we need to find out the structural resonance factor. So before that, for any of the force, wind force, to be calculated on any of the element, so this is a general formula for that. QH, which we already calculated here, and Q and GQ is a gust response factor, which we had find out from the table 4.2.4 as 1.9, and GX is a respective gust factor or resonance factor. We need to find out from various table which are listed here according to the materials or element which we are going to use, and Cx is a drag coefficient. So this is also depend upon the surface of the material, and another one is area. It may be diameter into length for conductor, and sizes in case of solid structures, and aluminum tubes or insulator, we need to consider the diameter and the length of the same. So these are the formula how to find out the wind forces on conductor. So likewise wind forces on insulator, wind forces on structure are given in this line of pages. Also this wind forces on poles we can consider for some aluminum tube structures. So next one is we need to find out the structural resonance factor. For that table 4.2.5 to be referred for conductors. So this table also we had extracted here. So you can see here for category 4. So generally it is given as a formula. We had applied the same formula for actual span of our conductor. So we can consider for one direction conductor, that is 100 meter, which one is maximum, and the formula is applied based upon this natural logarithm which is given here. It's a factor instead of adding all this value for several meter of span. So now based upon our terrain category 2 and conductor's maximum span of 100 meter, we are having 0.92 from the table which we had calculated. So similarly like for lattice tower, we need to refer table 4.2.2.4.3. For that we need to go page number 54 to be referred. So here we can see that GT is a structural resonance factor for lattice tower below 60 meter. This shall be taken as 1.05. For structures taller than 60 meter, GT shall be evaluate. So there is some formula to find out GT if the structure height is more than 60 meter. So right now we no need to check those formula now because our structure height is less than 60 meter. So for 60 less than 60 meter we need to consider 1.05. So we are considering the same. Next one is we need to consider the structural resonance factor for aluminum tubes and poles. So for that we need to refer class 4.2.2.4 notes, page number 56 to be referred. So here you can see for self-supporting steel poles, G pole will typically 1.15. So we are considering this. Also for insulator sets we need to refer table 4.2.2.4.2 of EN 50341, page number 54. So GINS is a structural resonance factor of said to be taken as GT or G pole. So we already calculated the G pole as 1.15 and GT as 1.05. We need to consider the maximum one. So we can consider 1.15 as a G ins, that is for insulator, structural resonance factor for insulator. Next one is a drag coefficient we need to find out. For that we need to refer class 4.2.2.4.1 for conductor. So page number 53 to be referred for that. So here it is mentioned 1 we need to consider, and conductor with ice cover we need to consider 1.2. So for this we need to refer page number 58. So here you can see that it is a combined wind and ice loads. In this, in the class, in the table 4.2.6, here you can see that CCL is a drag coefficient for conductor with ice. We already selected our conductor type is a soft rim, so the factor to be 1.1. So this value also we can add it, we can get from this table. So for soft rim it is 1.2 as per table 4.2.6 of EN 50341. So the same is extracted from the table. And for insulator sets, we need to refer class 4.2.2.4.2, page number 54 to be referred for that. So here you can see that drag coefficient for insulator set is 1.2. So we can consider the same value. Structures as per salt ratio, we need to arrived from figure 4.2.3 of 50341. So for that, page number 56 to be referred. So this is a solidity ratio figure to calculate the drag factor CT. CT1 is nothing but it is a direction where it is a face which is exposed direct to wind, that is windward area, and another one is downstream of wind, is called CT2. So based upon that, we need to get the value. We are assuming the salt ratio as 0.25. For that, we need to find the drag coefficient using this graph. So for 0.25, if I draw the straight line, it is going to meet at 2.55. So I am taking the same value here as an input for drag coefficient. Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.